Good morning, everyone. It is Fumihiko Matsuda from Kyoto University. First, I would like to express my sincere gratitude to the President and organizing committee for their enormous efforts to make this conference a huge success under a challenging COVID-19 pandemic situation. Also, special thanks to Professor Sadanori Akita in the scientific committee and my close friend, who kindly gave me this fantastic opportunity. I regret I cannot be on site due to the severe restriction of Japanese border control. I have no conflict of interest. In my talk, I will take 5 minutes to introduce the Rare Disease Data Registry of Japan, a national project to establish a platform for rare disease research. Then I go to the 2 topics on applying AI to rare disease research. Rare disease research is supported by the Ministry of Health, Labor and Welfare and AMED. The 110 MHLW research groups are responsible for establishing diagnostic criteria and guidelines, conducting disease cohort studies, promoting public awareness, and supporting medical practice. 190 AMED research groups aims to elucidate the etiology and pathogenesis, develop diagnostics and therapeutics methods, and improve medical care levels. They are working for clinical trials, studies to establish evidence for guidelines, genome and omics analysis, and so on. These 2 programs are collaborating to improve the medical treatment of rare diseases. Each research group has the responsible diseases and constructs its registry to collect clinical information and biomaterials and conduct genomic analysis in some groups. However, cooperation between groups has not been well established, and such valuable information has not become open to other groups and industries. Under such circumstances, we consider that establishing a platform that integrates decentralized information and promotes secondary use of these data will dramatically accelerate rare disease research. The keyword is data sharing in such an effort. During the study design process, we have repeatedly discussed how we can attract research groups to cooperate with RadarJ. It includes system design, an integrative information basis, information normalization, quality improvement support, and adding extra value to the registries. No one even knows how many registries existed when we initiated the project. We have conducted a web-based survey to collect detailed information on running registries and summarized the obtained information in our own website as shown here. Here is the information from our research group. You can see such information by getting access to our website. The registry system accommodates records and data of patients' personal information, clinical information, and genomic information separately. Regarding personal information, patient's real name is registered. Even if the doctor in charge changes or the patient moves, the name makes it possible to track them. Since Japan does not have a unique social insurance number, there is no other way. Only the research group's secretariat can manage personal information. The record is divided into several pieces, encrypted and stored separately to avoid information leakage risk. Clinical and genetic information is merged to conduct integrative analysis using the artificial intelligence platform. The clinical information to collect was selected to enable cross-disease analysis. The items were divided into 3 groups. We matched items in A and B to the standard items in GRDR, the Global Rare Disease Registry in the United States, and USARD, the European Union Committee of Experts on Rare Diseases. We have accomplished 5 work packages as shown in this slide. We regularly survey and disclose the information of research groups on our website. We define the concept and the policy of RADA-J. We constructed a registry system with quality assurance required by the government. We designed the system to fulfill ethical and legal regulations. Lastly, we have developed an AI-assisted analysis pipeline, which I will use the rest of my time to show the results. We established collaborations with 59 research groups and constructed a registry of 139 diseases containing more than 23,000 patients to date. 136 diseases correspond to 40% of 333 shitei-nanbyo, for which the government provides 100% of medical expenses. I have 2 topics applying AI to rare disease research. The first is a pathology imaging analysis tool for neuromuscular disorders, and the second is the identification of causative genes and variants in retinitis pigmentosa. This slide shows the classification of major muscle diseases. The first image shows nemaline bodies. Because of the presence of nemaline bodies, the disease is called nemaline myopathy. In the second picture, you can see the core-like structure in muscle fibers. They are called central cores, and the disease is named central core disease. We cannot definitively diagnose this disease without muscle pathology showing central cores. Likewise, we need muscle pathology for the diagnosis of nemaline myopathy. The third one is myotubular myopathy, as muscle fibers look like myotubes. The last one is central nuclear myopathy, as nuclei are located in the center of muscle fibers. All those diseases are categorized as congenital myopathy, defined by pathological features. As pathological features are almost always part of the definition in many muscle diseases, muscle pathology plays a critical role in diagnosis even in this molecular era. We therefore decided to establish a muscle pathology diagnosis assisting system using machine learning in collaboration with IBM and Dr. Nishino Ichizo at NCNP. We first aimed to establish differential diagnosis classifiers between muscular dystrophy and immune-mediated necrotizing myopathy using muscle pathology images with deep learning technology. Both MD and IMNM are pathologically characterized by necrotic and regenerating fibers. They look very much similar. The differentiation of these conditions is one of the current hot topics, as IMNM is treatable while muscular dystrophy is practically not. Many IMNM cases are misdiagnosed as muscular dystrophy, and patients have been left untreated. Therefore, a precise diagnosis of IMNM is vital. We collected image data of HE-stained pathology slides. About 1,000 each images were taken at the diagnosis. Dr. Nishino, one of the most experienced pathologists dealing with several thousand muscle images every year, cut out areas useful for differential diagnosis from the original images and created training dataset for deep learning. 4 classifiers were generated, and the performance was compared with clinicians. Surprisingly, all 4 classifiers returned a higher success rate than the most experienced pathologist Dr. Nishino himself. It is expected that doctors' score using HS stained images only is not 100% because they use other information than pathology to diagnose. Using a similar approach, we next tried to classify 5 different muscular dystrophies, namely dystrophinopathy, LGMD2A and 2B, UCMD, and FCMD. 561 HE staining images were used for classifier development. Myopathologists tagged annotations to highlight areas typical to each disease. Due to the time constraint, I will show you the final results. Newly developed classifiers again returned an average of 82% accuracy, while clinicians could achieve 58%. Physicians comprehensively diagnose neuromuscular diseases using biomarkers, skeletal muscle CT MRI, electrophysiology, and genetic analysis in addition to muscle pathology. Some of them are expensive and need equipment. On the other hand, HE staining is a standard histological technique. It is widely used globally, including in developing countries, because it is inexpensive and does not require advanced technology. In these countries, expensive examinations are not affordable. We strongly believe that introducing this classifier to such countries will contribute to the accurate diagnosis and treatment selection for neuromuscular diseases. We are constructing a platform that enables the generation of differential diagnosis classifiers simply by importing images. Such a platform can be applied to many other diseases that images provide helpful information for diagnosis. I now move to the second topic, how we increase the success rate of genetic diagnosis. Finding causal genes for monogenic or Mendelian disorders is essential to improve genetic diagnosis. However, the actual success rate using NGS technology is currently only 30 to 40%. We tried to develop a new method that efficiently pick up candidate genes with an AI-assisted algorithm using a next text mining approach, and we applied the technique to whole genome sequencing results. The process of finding the causative gene from genomic analysis results is shown in this figure. First, we look for a damaging mutation in known causative genes. If no such mutation is found, we search for a new causative gene. It is a tedious process to identify the causative mutation in many genes in the genome. On the other words, it is not that we cannot find a gene, it is challenging to find the right one out of so many. Retinitis pigmentosa is a rare and intractable retinal disease that causes vision loss, and genetic mutations cause most cases. 95 genes have been registered as a genetic cause of RP in RetNet, a database for inherited retinal diseases. Although RP shows a wide variety of pathologies, the relationship between causal genes and phenotypes is unknown. In 2014, we conducted a target exome sequencing of 365 candidate genes to identify causal genes and variants of 326 RP cases. We found causal variants in the known 30 RP-related genes for 122 patients, which is 37.4% of the cases. However, There were no causal variants for the remaining 204 cases. How we increase the success rate from 37.4 to over 70% is a critical issue. We introduced IBM Watson drug discovery to address this issue. It incorporates 10 million articles in Medline and discovers relations between genes, disease, and drugs. We used predictive analysis, a function in WDD that ranks gene candidates based on the similarity with those in the known gene list. Making an appropriate candidate gene list is the key to a good ranking result. We performed the whole genome sequencing of 523 RP cases, including 135 out of 204 patients in the previous study. The other 69 cases without grower consent, including whole genome sequencing analysis, were not included. Using the whole genome sequencing results, we made a candidate gene list of 1,025 genes based on possibly damaging mutations presented in patients' genomes. 34 were known RP causal genes, while 994 introduced RP in 423 control subjects as false positive. You may think we should remove genes presenting false positive in making a list. There is still possibility that the control population contains hidden RP cases. Hence, we kept all these genes as candidates. This is a result of the initial analysis. As you see, new candidate genes increased the diagnostic rate. However, around the 50th candidate gene, the false positive rate started to grow. We considered that this might be because of the effect of the top candidates in PA. So we took another strategy, which is to rank the genes, remove the top 20 genes from the list, and rerun PA. We repeated this process several times. This recursive method significantly contributed to reducing the false positive rate. In the top 50 candidate genes ranked by PA with recursive model, 17 genes were causal genes of other retinal diseases. It is known that 37 of 19 known RP genes cause other retinal disorders. 4 genes are in the same family as known RP genes. Of note, SAMD11 and LIP6 were not included in RetNet when we conducted the analysis, but were added in its latest version. Judging from these observations, WDD seems to rank candidate gene efficiently. The diagnostic rate in our previous study was 37.4%. 135 out of 204 undiagnosed carriers were examined, and 32 cases, or 23.7%, were successfully diagnosed. If we expect the same success rate from the other 204 samples, then the overall diagnostic rate would be 52.1%. This is a summary slide. We built an AI-assisted gene identification pipeline. Many top-ranked candidate genes shared structural or functional features with known RP genes. It successfully picked up recently discovered causal genes as strong candidates, suggesting that this approach works efficiently. The analysis pipeline could improve the diagnosis rate by 15% without increasing the false positive rate. However, the definitive proof of causal genes needs functional study, which is missing in our analysis. Construction of an analysis platform integrating the developed function is underway to apply the pipeline to other diseases. Limitations still exist related to the short-read sequencing technology, which is unsuitable for structural variation. Also, the detection of epigenetic effects and somatic mosaicism needs other approaches. Here is the list of research groups involved in the Registry project. And this is the list of collaborators in AI projects. We conducted the research with the support of AMED, MEXT, MHLW, and JSPS. Thank you very much for your kind attention.